All right, so this is the review for Energy Unit 5, Honors Physics. And to start with, just basic definition. The first section of our unit was about work energy. And the work energy theorem, in other words, as much work as you do. Let's start over. Energy can be defined as the ability to do work. And however much energy you put into a system, that's how much work can be done or stored. And however much work you need to be done, that's how much energy is required. So your basic definition, I guess, or helpful equation is just going to be that work is equal to force times the displacement of the object. And keeping in mind that that force is going to be parallel to the displacement. So first of all, right off the bat, just keep in mind that if there is no displacement, there is no work. So no matter how heavy something is, if you're holding it, if it's not moving, there's no work being done. So there has to be a displacement. And like I was saying, the force, the only force that counts is the force that's parallel to that displacement. For example, let's say you have a hill or like an incline, and you have this 50 Newton block. So the weight of this is going to be basically 50 Newton straight down. So that's just the weight of the block. And the incline, the hill or whatever, is let's say 15 degrees. Okay. And you're going to go up to a height of, let's say, 5.2 meters. All right. The ramp is going to be 20, let's make it 20 meters long. Okay. So just to show, make sure we got what's going on here, the ramp itself, 20 meters long. The height of the hill from top to bottom is 5.2 meters tall. Okay. And so, question I might ask first, what is the amount of work done pushing the block up the ramp? So word. How about if I say this right? Work done just up the ramp. And for that question, you really just want to know, okay, we're going up the ramp. So let's say it's being pulled or pushed with a force of, let's say, 25 newtons. So the weight of the block is 50, and you're just pulling. There's friction, there's all sorts of things involved, and so you have to pull kind of hard. And so let's just say, again, 25 newtons just to make it easy. You are pulling up that block 20 meters with a force of 25 newtons. And so it's pretty straightforward. The force is, again, work is force times distance. And so the amount of work that you did was, the force is 25 newtons, and the distance or displacement was 20 meters. And so that gives us grand total of 500 Newton meters. And if you remember, Newton meters is joules. Joules is the unit of work and the unit of energy. It's the same thing. It's if you remember, the energy is equal to the work, and I should clarify that work is going to change the amount of energy, either the amount of kinetic energy something has or the amount of energy that's stored. So it's going to be the same unit. Okay, now that's right up the ramp. Now the question is, what about how much work was done against gravity? Well, that's a different question, because that ramp could, there might have been a lot of friction, it might have been not a lot of friction, it doesn't say. But the point is, you lifted that box up a distance. So if I say, what's the work done against gravity? All right. So again, to clarify the two different questions, you're pulling this up a ramp. It doesn't matter that it's a ramp. You're pulling it a certain distance. And because you're pulling it a certain distance, just up this ramp, what is the work done up that ramp? Now, because it's a ramp, we can ask this other question. Well, how, you lifted it 5.2 meters up. So how much work was done by lifting it up? Different question. So in this case, it's the same equation. Work is force times displacement. But, there we go. A little technical glitch. But work is force times displacement. And the force is now, like this 50 Newton block, that you're fighting gravity for that 50 newtons. So that's the force you're fighting against, this one that's straight down, parallel to the displacement that you're about to do. So you're lifting this block using a ramp, and it's a 50 Newton block. You're going up 5.2 meters. So the displacement is 5.2 meters. And so the work done here is 260 joules if you multiply that out. All right. So notice the two different questions. There was angles asked involved, but I didn't have to do anything with the 15 degrees. There's two questions: the work done up the ramp, the work done against gravity. Done. Boom. Okay. So because we had all the information. Now, there is a question on the review guide where you have a woman. I'll just put this right here. Sure, it's up there. There we go. So number 4, you have a woman walking your dog. Okay, suddenly the rabbit pops out of a bush. The dog freaks out, and the dog starts like pulling the woman down the street. They're gonna end up going 17 meters, and she's pulling on the leash, 21-degree angle, and there's 122 newtons of tension. And so the question is going to be, how much work did the woman do? All right. So now you got to understand, if you could picture this, I should say, scooch this up a little bit. We now have a situation where we've got the leash being pulled at a, just double check, 22-degree angle, I want to say. 21-degree angle. So a 21-degree angle, all right? And there is 122 newtons of force on that leash, all right? So she's pulling the dog backward. They're all moving forward. They're moving in this direction. She's pulling backward, all right? So you could say this is going to be a negative 100 because it's opposite direction of the movement. She's pulling against the movement. So question is, how much work was she doing? Well, the direction of the leash she's pulling is not parallel to the direction that the dog and the woman are moving. So you had to figure out, we got to figure out the horizontal component of this. And if we look at it, this is just a right triangle. And so we need to find out the adjacent side. And the adjacent side, if you do so ka toa, so it sounds like ka, that means cosine. And basically what it boils down to is negative 122 newtons times the cosine of the angle 21 degrees. And that tells us that the force was negative 113.9 newtons. All right, so that's how she was pulling, is negative 113.9 newtons. And again, the negative is because she's pulling backwards against the direction that they are moving. So now we have the horizontal force. So work is just the force times the displacement. And so now the displacement is to the side. We've got the force she's pulling to the side. And we just plug our numbers in and get this. So the force is negative 113.9 newtons times the displacement, 17 meters. And so our final answer is negative 1936 joules. Okay, and it's negative because she's working against the dog, the direction. She's pulling against it. So it's negative. Okay. So that's work energy. Just again, work is equal to the amount of energy the amount of work done will change the energy. It will either take away energy or add it. It could be storing energy, so gravitational or elastic, or it could be changing the kinetic energy of the system. So it could be speeding up or slowing down. Again, taking away, speeding up would be adding energy, slowing down would be taking away energy. Okay. So let's see. Now, the second part, I'm just going to switch to another page just to keep this clean. The second part of our unit is about, where's my green pen? What did I call it? It's just the types of energy. So let's call that, I could have called it energy types, but I'll just add an extra word that I'll spell wrong. Types of energy. And of course, that's going to be your, what other fancy pens that I got over here? Ooh, orange. Let's do orange. So we've got our kinetic energy, of course. And kinetic energy, if you, I'll just write the equation. It's 1/2 mv squared. So if there's one word that goes with this that reminds you of it, it should be something like motion or moving. I'll just write motion. Okay, there has to be motion. If there's no motion, if they're sitting at the top of a hill, if they're waiting against a spring, if they're not moving, there's no kinetic energy. All right, and then we have PE, we'll start with G. So that is gravitational potential energy. That's energy stored because it's up high, or like because of a height. So that is mass times gravity times height. And again, if there's one word to think about what it has to do with, or in our terms here, I mean, we can expand upon it later, but right now it's, I'm going to spell that wrong. Height? I think I spelled it right. Okay. And finally, PEE, elastic potential energy. That is going to be 1/2 kV squared. And again, if you think of anything, it's like springy stuff. I'll just put springs. But that could include rubber bands, anything stretchy like that, that you could basically store energy in. So now let's take a look at a question that we've got. Gravitational potential energy. So one thing you should do, make sure you got is, I'll just put this right here. At the very beginning of the energy review is this data table. Make sure you got all that like down pat. The ability to just instantly recognize gravity or height or any displacement. There's a couple more, mass, velocity. You need to be able to do that. In other words, you should know what all these letters are. All right, especially and including K, not especially, but including this K, the spring constant, or K value, it's sometimes called. And so if you could do that, these are going to be a piece of cake. So you're going to see questions like, how much energy did this car have if the mass was blah, 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 and it was moving at certain speed? Plug in the numbers and you got it. All right, that's really all there is to it. So I'm not going to belabor that. I think that's something that you can handle. And if not, let me know tomorrow or in the near future, and I could handle, or we could talk and I get you there. There is another equation, and I'm looking over my little notes here. So where did it go? Oh yeah, it ended up here. It's this one. Force is KE. So this is the this involving K again. So it's involving force of a spring force of a spring. So that's your K value and the distance that it's either stretched or compressed. And again, it's a pretty simple equation. So we got a question, let's see, question 12 on the review guide. It says, scooch that up there. So by the way, this stuff right here, great thing to put on your note card. All right, I'm not going to tell you what to put on your note card. You decide that for yourself, but I mean, hint, hint. So, all right, so question 12, how much force is needed to compress a spring 0.4 meters? Okay, so how much, let's just go, the distance is 0.4 4 meters, and the spring constant, or K value, is 40 newtons per meter. All right, so question 12 is asking how much force. All right, and then question 13, you might be like, it's the same question, but then you look, it's like, oh no, it's asking how much energy is involved. So 2 different questions, 2 different equations. So for question 12, you're going to use the F equals KD, and you literally just multiply those 2 numbers together. All right, I'm not going to do that right now. You could handle that. 13, it's asking for energy. So we're going to do PE, the elastic potential energy, 1/2 KD squared. So you're going to use that equation with these 2 numbers, and you'll get the answer. Okay, so 2 totally different questions. Now that's the mathematical take on all this. These were derived from the graphs, and we did the graphs a long time ago when we did those stretchy springs. So I want to move on to those though, because the graphs are where it all started, and you are going to see graphs on the test. So I'm just opening up the review guide. I guess I could put it here. So here we have a graph, and it is a force versus compression graph. In other words, you got a spring, and you're just, it's measuring the amount of force it took to compress the spring a certain distance. All right. So whenever you see a force versus compression graph, or a force versus, I guess you could say, tension graph, where there's a, like you guys did, a stretch graph, anything involving a spring, there's, well, 3 things you could do. One of them is not asked in the review guide. And it would ask, like, how much force is required to stretch or compress a spring like a certain amount of distance. And like, so I could ask how much force would be required to stretch the spring 1 meter. So I'll just go over 1 meter, and I go up, and I'd be like, oh, it looks like, and you can read it, looks like it's about 25 newtons of force. So, you know, I could ask that. That's one thing you could do, just read the graph. And then there's 2 other things, and those are represented by question 15 and 16. The K value, or spring constant, of the spring, I'm going to write this in red because sort of important graphs, something to remember, and this might be something you put on your note card. Spring constant is, you're going to find the slope. Okay, so you find the slope of that line, that's going to give you the K value. K value here, find slope or the K value. Okay, can you read that? I don't like it, but whatever, it's my handwriting. The other thing you could do, what's another good color I got? I don't know, purple? Let's do this, do blue. The other thing is, how much energy does it take? So you've got a graph, and the amount of energy is literally just area under the line, okay? So if you want to find the energy, find the area under the line, and this, so what I mean by that, I'm going to keep it blue, is you've got, let's say, oh, and you got to be specific. Don't just like find the area under the entire line. Let's say it's this one says 1 meter, right? So for 1 meter, I'm going to just go up to 1 meter on my graph. And so I'm going to just kind of mark this there. That's 1 meter right there. And so I'm going to find the area under this line, and it is 1/2 base times height is the area of a triangle, in case you forgot. So a little box to make it somewhat more clear. 1/2 base times height. It looks like 1/2 b. It's 1/2 base times height. It's the area of a triangle. All right. So if that's not clear, let me know. I will clarify that for you. So you find the area. That'll tell you how much energy is in that spring if you stretch it, compress it in 1 meter. All right. So it might ask a different distance, but watch out for that distance. It is important. If you were to find the area under the entire line, you get it wrong. So that's not what the question's asking. So just watch out for that. All right, not seeing any questions. Anybody there? All right, well, if you are, let me know. So then I'm not going to do 17, but this question didn't copy very well. And so if you look on the OneNote, it's definitely like more colorful. You can tell which track is which, but just think back to when we did the marble races, just as a demonstration at the beginning of class. All right, we want to know, first of all, they're going to have the same starting height, and so that means they're going to have the same starting gravitational potential energy, which means they're going to have the same kinetic energy at the bottom when they get to the bottom. And since they have the same kinetic energy at the bottom, they're going to have the same speed at the bottom. Okay, bottom line. Now, which one gets there first? Well, this one will get there first because it gets to top speed the quickest. All right, the other ones are like taking their time. It's going slow, 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 slow. Oh, I'm going to go to top speed. So, like, different question. Just think it through. All right. All right. So, talked about the equations. Oh, total mechanical energy. Add them all together. So, going back to, let's get rid of that. Okay. Going back to those equations in orange. Not so much orange, but like these. No, I already used green. Dang it. Purple. Purple it is. All right, so if I add these together, let's do it over here. So those three together, sum them for the total mechanical energy. All right. A lot of times in these situations you're going to see in this class, you're going to have 0 plus some number. You know, like a lot of times there's not going to be elastic or something. So, but you sum them all up, that's going to give you the total mechanical energy. All right. I think that's about it for the types of energy part of the unit. And finally, well, different shade of green is Servation of Energy. And that is the energy. That is the idea that energy cannot be created or destroyed. It's going to be transformed from one to another. Let me rephrase that. In every situation in real life, there's going to be thermal energy. There's going to be energy like transformed into heat, and so it will be lost to the system. In a lot of our situations here, we ignore that. So it'll be kind of, it'll be very clear if there's going to be friction involved or not. It's pretty safe to assume there's no friction unless it says there's friction. So, what if I put that up there? Yeah, conservation of energy is what I've been talking about. So when it comes to that, let's take a look. I get to see the back of my head a lot. All right, let's take a look at this question right here. This question right there. All right. So number 19, we've got a 1,300 kilogram, apparently car. There's a couple, all right, there's a weird typo. Moves up a hill and coasts to a stop at the top of the 7-meter tall hill. We want to know the initial type of energy. All right, I hope it's fairly obvious that it is kinetic, and I'm not going to write the whole word out. It's kinetic energy because it says right here, the initial velocity is greater than 0. All right. The height is 0, so there's no gravitational energy. And there's absolutely no springs involved that we could tell that it's mentioning, so there's no springs. What's the final type of energy? Well, the velocity is 0, and the height is 7, so it's going to be PEG. So just, basic stuff like that. Like later on, you're going to see, okay, we got some spring energy in this question, and you just read the question, and it should be clear. But if not, let me know. So what is the amount of gravitational potential energy at the top of the hill? Well, again, pretty straightforward. This isn't conservation of energy, but at the top of the hill, PEG is equal to mgh. And I'm squeezing it in here like I tell you not to do. You really should be doing this on a separate sheet of paper so it's a little bit more clear, but well, I've already started. And so that's going to be the mass of the car is 1,300 kilograms. Times gravity, which is 9.8 newtons per kilogram, and the height is, it says 7 meters, so again we'll do that, 7 meters, and when that all multiplies together, my handy dandy cheat sheet. That will be big number. I got, yeah, 89,180. And then the units cancel out in such a way where it's going to be, well, here, kilograms cancels out, and we're going to be left with Newton meters, which is joules. All right, so that's how much energy it has at the top of the hill, how much gravitational potential energy it has at the top of the hill. The amount of kinetic energy at the bottom of the hill, well, it doesn't give us enough information here. Kinetic energy, it says the velocity is greater than 0. We need a better number than that to calculate it, or we just use our knowledge of conservation of energy. And we know that, well, all this gravitational potential energy that it got over here it came from somewhere. Where did it come from? It came from the kinetic energy that the car had. It's just like your mousetrap rolling up the hill, up the ramp. Where did it get that energy? It came from the kinetic energy. So the amount of kinetic energy at the bottom of the hill is going to be 89. This is why I don't want to squeeze it in there. 180 joules. I didn't need to do any calculations. It just is conservation of energy. So now I can figure out the velocity because I can use that equation. So I'm gonna squeeze it in there. It'd be nice if I had it on the screen. I'm gonna squeeze it in there. So let's see if I can do this. So I'm gonna start with, all I know is that it's got kinetic energy. So the kinetic energy is equal to 1/2 mv squared, right? Right. So I want to know the velocity. All right, so this is where it's going to get a little yucky. Tell you what, let's just scoot this over. Okay, so kinetic energy is equal to 1/2 mv squared. And I want to get velocity. I want to know the velocity. And so I need to get this velocity by itself. I'm going to divide both sides by 1/2 m. So that's going to cancel that out on this side. And whatever I do to one side, I have to do to the other, 1/2 m. So that gives me kinetic energy divided by 1/2 m is equal to v squared. Now, that's v squared. I don't want v squared. I want v, velocity. So how do you get rid of a square? You do the opposite. You take the square root, and whatever you do to one side, you have to do to the other. So that gives me velocity is the square root of kinetic energy divided by 1/2 m. Okay, so I'm going to use that equation to solve for velocity. And you got to be careful in your calculator. Okay, so you put the numbers in, you just put that 89,180 divided by, I mean, you could rearrange this to whatever you're comfortable with, but this is just pretty raw. Put it in your calculator correctly, you're going to get the correct answer. And that correct answer, according to something I figured out earlier, is going to be 11.7 meters per second. All right. Now, you got to put it in your calculator correctly. Common mistake is to do everything correctly and then not careful with the order of operations in the calculator. So if you're having trouble with that, let me know, let somebody know, and I'll show you how. It involves, well, there's a couple ways you could do it. My favorite way is parentheses, but I'm not going to show during the live stream. We could talk in class. That's just a different type of skill. That's not really physics. That's just computation. Okay. Now, that's about it. Okay, so that's conservation of energy in a nutshell with one question. All right, there's obviously other examples. In this case, we start out with elastic. We get to, gravitational and velocity, kinetic. So let's move on though. I want to talk about these. Get this out of here. These. All right. First of all, I'm going to tell you, what's it called? It's called 5.3 practice, and specifically conservation of energy. If you haven't done that one, do it. There's questions on there that should have probably been included on the review guide, but weren't. So it involves drawing the bar charts. So make sure you're very comfortable with those bar charts, the energy bar charts. This one right here is bar charts, but you can see it's missing like some detail. Like it doesn't differentiate between elastic potential and gravitational potential. It just assumes there is no elastic. So do that practice. Look at it, make sure you're comfortable with it. You might have already done it, but go back and review it. Go back and look over it. All right. So for this one, we got a ball drop from a bridge, and it caused a small amount of air resistance. The final state of the ball is the instant before it strikes the water, meaning the initial type of energy is basically at rest before it's dropped. The final, what is it saying? The final state of the ball, the instant before, the final state of the ball is the instant before it strikes the water. It's saying that as the ball falls, the instant before it hits the water, that's the final state that we're talking about. Okay, so it hasn't hit the water yet, but it's like literally just about to. So this energy bar chart, to start with, the initial stuff is, again, there's no numbers given, so I'm just going to fill in, no, I don't have it. So I'm just going to fill in potential energy all the way to the top, because it's got that much. I mean, it's just all full of potential energy. It hasn't started. It says it's dropped from rest, so it hasn't started moving yet. So there's zero potential or zero kinetic energy. It's all potential energy. Now it says there is a small amount of air resistance. Let's do this in purple, because air resistance, as everybody knows, is purple. Okay, so air resistance in purple. And what that does, remember, air resistance is going to slow the ball down. All right, and anytime you're slowing something down, you're removing kinetic energy from the system, and it's not being stored anywhere. Okay, it's being taken away, and we call that work. Going back to the beginning, and so the air resistance is doing a little bit of work, negative work, on the ball, and that's going to have it's not destroying the energy, but it's taking it out of the system. And so when we get to the end, just before the ball hits the water, there's no height, so there's no potential energy. This will just be basically zero. But the ball is definitely moving its fastest at this time. Unfortunately, it lost some energy because of the air resistance. Okay, stupid purple air resistance. It took some energy out. So it's not going as fast as it could have, I guess, you know, if there was no air resistance. But that's just how it works. That's work. That's the work I'm talking about. In this case, it's negative work. Now, I don't know, if there was a wind blowing it downward, then maybe you could have positive work and it would be speeding it up. But that's not good. That's a weird example. One more, and then we'll call it quits. I haven't seen any questions. Hopefully that means you guys are just doing great, and doesn't mean I'm having a huge technical error and this has all been a waste of time, but I don't think that's the case. Everything looks like it's working. So we got a similar situation, not similar, but we got another situation here where we've got a Hot Wheels car started on a ramp, and it rolls down and here, and then there's friction, and eventually slows down to a stop here just because of friction, not because of anything stopping it, except for the friction and air resistance. So from A to B, and I hate to do this one for you, but this is why I'm doing this. Just make sure you get this right. From A to B. So if you want to do this on your own, pause this, or look away, or just whatever. Put your ears in your fingers in your ear. So try this for yourself. From A to B, it starts out at the top, and it's not moving. So it's not moving, so it's going to have zero kinetic energy, and it's going to be all potential energy, just like the ball being dropped. Okay. Friction is there, and so purple, friction, slowing the car down, doing negative work, taking energy out. Nothing's, oh, no. Hang on, stop. No, that's right. So there's friction, okay? And so what happens is, now you might have a question about gravity. If you do, you could ask me tomorrow. I'm not going to explain it right now because I don't want to be confusing. Because gravity is already, I'll just say gravity is already taken into account when we talk about gravitational potential energy, okay? So friction is slowing it down though, and that's not taken into account except for this spot right here. That's why we got to do this, because we're taking into account friction. So friction is doing work, it's slowing it down. And so when it gets to B, basically the bottom of the hill, it's just like the ball being dropped above, above the water, and ooh, that's not friction. How dare I do that? It's just kinetic energy. And doesn't come quite to the top, and it's a sloppy bar graph, but point is it's all kinetic. There's no potential anymore. It's all the bottom. Okay, so now from B to C, in B it's all kinetic. In fact, we just wrote that. I just represented that with bar chart, just like this. Okay, and there's no potential because it's still not on the hill, because it didn't magically become like up on a hill. It's now at B. It's at the bottom of the hill. It's moving. It's got kinetic energy. It doesn't have as much as it could have because of friction and air resistance. But then between B and C, it slows down to a stop. Stop. No height. Okay, so it stopped. There's no kinetic, so that's gonna be 0. There's no height, so that's gonna be 0. What happened to it all? Well, you probably already guessed it. But work took away all the remaining energy. The friction did work and took away all the remaining energy. So that's it. Negative work takes away energy. Positive work would speed it up. All right, so if it was speeding up, if something, let's put this way, if something external were pushing on the car to speed it up, that would be positive work. All right. So that's basically it. What do you put on your note card? I don't know, whatever you want. These equations. The first equation, I'll slide back one page here. Okay, to see what I'm talking about. These two things right there. Maybe that's something you put on your note card. How to deal with a triangle. I mean, again, whatever you want. It's not a memorization type of test, so it's not like you're gonna be cheating. You can't write test questions on your note card or anything like that. Okay, so that's about it. I'm gonna wrap this up. And if you do have any questions for me, just let me know. Send me a remind question, or just talk to me in class tomorrow. And good luck and good night.